So we will do the steps for the layout. I have opened the terminal window and I have opened the command virtuoso ampersand. The virtuoso window has opened. So even for this layout also, you're supposed to make a schematic symbol and the test circuit. So I'll go to File, New, Cell View. Right, a new cell view window will open. So before that you need to select your library, give the cell name as inverter underscore layout, just to identify that you are doing this schematic for the layout. Click on OK and make the schematic circuit for this. So for this procedure is same. Go to create instance, browse, go to GPDK 180, select PMOS, place it, then select NMOS. But in this case the PMOS is 2 times NMOS, so the width you're supposed to give it as 4U, right, and place it. Likewise select NMOS and don't change any value, it will be 2U, right, and place this NMOS just below the PMOS. So the width of the PMOS is twice that of the NMOS, right? So NMOS is 2 times, PMOS is 2 times that of NMOS, and complete the connection from here. I have placed the V-in, VDD and ground pins. I have made the V-out pin as the output and I will place it here. And next is the wired connections. Complete the connections using the wire and click on check and save. So your schematic will be saved. Then create the symbol here, create cell view from cell view, and it asks for the options. So these options you know. So you get this, rename the center part and click on check and save. So the symbol will be saved with no errors. Then from this you have to create the test circuit for the layout also. Go to File, New, Cell View. So you give the name as inverter underscore layout underscore test and click on OK. So here create the test circuit. Anyway, the creation of the test circuit has already been explained in the previous thing. So go to your library, then click on this, the first option, that is INV underscore layout. So from this library you're supposed to select this. By default the symbol will come. Close this, hide it and place the symbol here. So regarding the symbol I had told you earlier, so you can create the symbol or you can retain the same thing. So in this video I'm just retaining the symbol as it is, and I'll give the parameters. So same values for V pulse I'm giving, and I'm placing it near this V in. Now I have selected VDC with the DC voltage as 1.8. Rotate this and place it near the VDD. Then you need a capacitor with the value 0.1 pico. Place this near the output and we need to complete the connections. I have placed the ground and I have completed the connection, which will look like this. Now save this test circuit and you have to get a message, the test circuit saved with no errors. Then continue with the next procedure as it is, that is go to launch ADEL. You'll get the analysis window. Just like this, setup, model libraries. You unselect 45 nanometer and 90 nanometer, and only the 180 nanometer has to be selected. Click on OK. Then go to analysis, choose transient, you give 100 nano and click on moderate and click on apply. Once you click on apply, that will come on this particular thing. Then you go to DC, click on save DC operating point, go to component parameter, click on select component, and you need to select the input, that is V pulse, and double click on this DC. Come back to this window, give the start time as 0 and stop time as 1.8, the same procedure. Then click on apply, and once you click on apply, the DC parameters will also come here. Click on OK. Right now you go to outputs to be plotted, select on design. So I just forgot to name the input and output line. I have renamed it. I have added the name as V in and V naught. So I'll just quickly go to outputs to be plotted, select on design. I'll click on the input line as well as the output line. Then those two parameters will also be shown here. Then directly click on netlist and run. You don't have to do the parametric analysis for this because layout doesn't need it. Directly the question which is asked is the PMOS is twice that of NMOS. So no parametric analysis, directly click on this button, netlist and run, and you'll get the transient analysis as well as the DC analysis like this. So split this transient analysis. So once you split the transient analysis, you will get a high for every low. The top one is V in and bottom one is V out, and right side is your DC analysis. So you need to do the delay calculation and the intercept calculation for this, just like how you did it. Like you need to go to the tools calculator and send V out V in value to the calculator, V out value to the calculator. So I have selected delay and I have sent the values from the graph. That is signal 1 should be from V in and signal 2 should be from V out. Rest of the values will be same. The threshold value will be 0.9. Edge number 1 and 2 will be 1, and edge number 1 is rising and edge number 2 is falling. Click on apply. You will get some equation, and click on run button as it is. So this will be your TPHL. Similarly, you are supposed to calculate TPLH also by changing the rising to falling and falling to rising, and click on apply once again. A new equation will come. Click on this run button. Right. Okay, so these two values. So first one is the TPHL and second one is the TPLH value. Note down this values. Right. Once you note down, then select intersect here, just like how you did it before. And why only two values is because you don't have 4 different values, and for layout it is only 2 values. Why? Because PMOS is twice of NMOS. So similarly paste the signal 1 with the from the graph of the DC and signal 2 from V out of the DC. Yeah, I have the signal 1 from the DC of the graph. One is signal 1 is from V in and signal 2 is from V out. Click on apply. You will get some equation, and click on this result button, and this is the intersect value which you need to note down. Right. Okay, so first you have to note it down. The value of delay and the value of intersect is different for the analog, and it is different for the layout. So first you have to note it down for the analog values. Then once you note it down, what you do is go to session and click on save state. Right, you need to do this. So once you click on that, you will get a window where you have to go to the cell view and click on apply and OK. Right. So why you are supposed to do this is because once you do the layout, you don't have to give the values once again. Right. That's why you have to save the state. Once I go to that window, you'll get to know why we have used that. Right. Now I will close this window. I will close this also. These windows, except the schematic window and the CDS window, you have to retain and continue from here. So you have to do the layout from your schematic window. So in your schematic window, go to launch layout XL. So by default you'll get these two things. One is create new and automatic. Just click on OK and just see that it will be from your library, nothing else. Click on OK. So once you click on OK, a new layout window will open on the side like this. So I'll just maximize this layout window. First you're supposed to go to connectivity, generate all from source, right? So in this you just go to IO pins and see whether all the pins are present here. If you want, you can just select this one as an optional pin label, create pin, go to options and change the height if you want, but as of now let it be 1 itself. Let's not change anything, just click on OK. So once you click on OK, you can see the NMOS as well as PMOS along with the pins. The top pin is VDD, bottom is ground, left one is V in and right side is V out. If you want to view the source, substrate and the gate and drain connection, you need to press Shift F on your keyboard. If you press Shift F, you can view the terminals of the source, gate and drain, right? But as I mentioned, you also have one more terminal called as the substrate. So if you want to view that, select the PMOS first, right click, go to properties, right, and you have an option called parameter, and then you have something called as a body tie type. You need to click on integrated, right? Integrated option you will select once the source and substrate is connected. Okay, then click on OK. So you can see the substrate terminal also. But if you just click on the detached properties, if you go to body tie type and select detached, it will be separated. This option you will be selecting if the substrate is not connected to the source. But now I want it as integrated, so I'll make it as integrated itself. Detached you'll use it somewhere else, so I'll just click on OK. Similarly, I'll select NMOS also. I'll go to properties, under body tie type I'll make it as integrated and click on OK. Right now you have to extend this PR boundary, the box which you can see here, you call it as a PR boundary. So if you want to extend it, click on yes on your keyboard, the letter yes. The cursor will change like this. So bring this cursor closer to this. Okay, so press yes, bring the cursor closer and slightly drag it on top like this, and this one also slightly bring it here as much as required. Then press escape. I'll bring this PMOS on the top at the center like this, and this NMOS has to be exactly at the bottom of PMOS. Once you get the straight line like this, you can place it. Okay, now your PR boundary is conveniently sufficient. So now the pins are scattered, so you need to do the pin placement. Go to place, click on pin placement, right? So VDD and ground has to be at the top and the bottom. Okay, first I'll select VDD. Under edge it should be top, VDD is on top. Then click on apply over here, then select H rail, right? Then go to ground, the edge should be bottom, then click on apply, then click on H rail. So this H rail you're supposed to do only for VDD and ground. Okay, so once you click on H rail option, the pin will expand. But for V in and V out, no H rail, just the edge should be left for V in and apply, that's all. And V out, it should be right and just apply and close this, right? So V in and V out, V in will be on the left, V out will be on the right. VDD is on the top along with the H rail, and ground will also be at the bottom along with the H rail. Horizontal rail is H rail, so it will expand, right? Now you need to complete this layout looking at the schematic. So if I open the schematic, right, so this is your PMOS, and if you click on NMOS will also be highlighted and the corresponding pins are there. Since the source and substrate are connected, we have given it as integrated. If it is not connected, we'll be giving detached as I mentioned. Now VDD is connected to the source of the PMOS, and ground is connected to the source of the NMOS. That connection we will make it in the layout, right? On the left side you have the so many layers. Select metal 1 drawing because we have to connect the metal pin. Then go to create shape path. The cursor will change. So as I told you, so connect from VDD to the source. Just click on that. You don't need to drag it, slightly move this connection and complete this connection here. You need to click on the enter on the keyboard. The connection will be terminated. If you click it from your mouse, it will just move left and right. Second connection is from the ground to the source of the NMOS. Okay, just in case if I click it, it will just move left and right. I don't want that to happen. So simply I'll just extend it and I'll click on the enter to terminate this path. Okay, these two connections we have done, right? So we did this connection as well as this connection. Next connection is drain to drain connection. I will do that drain to drain connection. This is your drain. So from here I will make the connection till here and I'll click on the enter. Okay, one thing we need to keep in mind is there should be no mismatch, which means the path what we gave here, it should not be overlapped. So I'll just press escape and I'll click on this and slightly I will move it inside so that it will come within the boundary of the drain. And if I do so, it will be slightly moved here also. So here slightly I'll just move the transistor so that I'll keep it aligned. See that there won't be any mismatch, right? Okay, so we did drain to drain connection and the next connection is from this connection to the output, right? So I'll go to metal 1, I'll create shape path once again, and from this connection I have to connect to the output pin. So again here there should be no mismatch. I'll click on this pin and I'll slightly move the pin exactly on the connection. Complete this connection so that there won't be a mismatch, right? Okay, so till here we have done it. Next we need to do the gate to gate connection. Okay, but here as you can see the gate is polysilicon. The other layers were metal layers. This is polysilicon layer. So what I'm supposed to do is in the layers, click on poly drawing, go to create shape path, right? Then come to the polysilicon part and click enter. Now I have to see that there won't be any mismatch. So I'll just move this connection to the left side and see that it is not overlapped. The overlapping is proper on both the sides. So here also a slightly mismatch is there. So I'll see that there won't be any mismatch and overlapping will be proper on both PMOS as well as the NMOS, right? Now there is no overlapping. Okay, only one connection is pending, that is the input. So from the input you are supposed to connect to gate connection, but the thing is this one is poly and this one is metal and you cannot directly connect the metal to the poly. So what you have to do is you have to go to via. So you need to go to create, go to via, and the connection, which means the via definition should be M1 poly 1. Why M1 poly 1? Because you're connecting metal 1 to poly 1. So this via definition you're supposed to give. Click on hide. So you'll get M1 poly 1 via like this, which has a combination of both metal 1 as well as poly 1. So I can place it here and from the poly I can give the poly wire, but instead of that I'll just merge with this polysilicon wire itself. Okay. Then I need to take the metal 1 and from the VIN I have to connect to this via within the boundary of metal. So what I'll do, I'll go to metal 1, create shape path. Then from this metal boundary I will complete the connection to the VIN. And now again I have to see that there won't be any mismatch and the overlapping has to be fine like this, right? Now your layout connections are complete. Let me just save this. And to check for the errors, you have a platform called Assura here. Go to Assura. You need to check Assura run DRC, run LVS and run Quantus. Click on run DRC. The technology has to be GPDK. So we will set this GPDK path for you. You can ask us. Okay, but still if you want to know the path for setting that technology file, you go to Assura technology. This is optional, you don't have to remember this. So I'll double click on this. I'll go to installs, Foundry, then analog and 180 nanometer. And under that 180 nanometer, select this Assura Tech Lib and click on OK if you want, and just click on OK. This is an optional step. We will just set that for you. Now go to Assura run DRC. This technology of GPDK 180 will come. So this is compulsory. Then click on OK and wait for the DRC run to get complete. And you should get a message, no DRC errors found. This is the first step. Next, again go to Assura, click on run LVS. So DRC means design rule check. It will just check for any spacings which is there. If there are any DRC errors, you need to just change the spacing and until you get the message DRC run complete. Next, click on run LVS. LVS stands for layout versus schematic. Even here the technology has to be GPDK 180. Click on OK. What LVS does is it will compare the layout along with the schematic which you have done, and it has to give 0 mismatches like this. You need to get 0 mismatches. If there are any errors, you need to just recheck your layout and you have to proceed until you get 0 mismatches. And you will get a message, layout versus schematic match, like this. Schematic and layout match. Third one is go to Assura, click on run Quantus. So it will ask for some options. Okay. First thing is, under setup, the output has to be under extracted view. Next, come to this extraction. Extraction type should be RC. Reference node should be GND, which is ground. Okay. Then scroll this down and you need to unselect this enable HRCX. Then you click on OK and wait for this Quantus run to be completed. So you need to get this message, inverter layout completed successfully and view should be AV extracted. So once you get this Quantus completed, you can close this. You can close this window and you can close the schematic window also. Just to see that the Quantus is complete, what you can do is you can go to file, click on this open, under your library, click on this drop down and you will get this option AV extracted. So if it is completed only, you will get it, or else you will not get this. Click on this AV extracted and just click on OK, and this is the extracted view that you can see. And if you just zoom in, you can see something called as pre-resistor, you can see something called as a capacitor and all. Okay, but it is not visible. If you want to see this, you have to click on Shift F. Then you can see this capacitance. You can just view this value and you can view the value of the resistances also. Alright, this is your extracted view. Now you close this extracted view. There are certain steps which you have to follow from here. So in your CDS window, go to Tools, go to Library Manager. So in your Library Manager, you have to select your library. Right? Select your library. Then select test circuit of the layout. And schematic has to be selected. Then go to File, New Cell View. Okay, File, New Cell View. Then the type has to be config. Select the type as config. Then click on OK. Then go to use template. Name has to be Spectre. Search for this Spectre. Name has to be Spectre. Click on apply and click on OK. Right? Then view has to be changed from my view to schematic. View has to be changed from my view to schematic and click on OK. So once you do that, you have two types. One is called as a table view and one more is called tree view, right? Come to this tree view, and this is the IO file, that instance what you had created earlier. Just expand this. Only you can see the NMOS as well as PMOS. So what you can do is right click on this IO and click on set instance as AV extracted. So rest of the things will also come. Okay, so once you do this, click on save, then go to open here. So once you click on this open, the test circuit will open. Double click on the symbol of the test circuit, right? So it will ask, the view will be AV extracted, then just click on OK. Now your AV extracted view will open after following all these steps, right? So for this, you have to do the analysis, where you have to go to launch, click on ADEL. The ADEL window will open. So again, you don't have to give all the parameters. So directly you can go to session and click on load state. Earlier we had saved the state. Now we are loading the state because same parameters we want. So if you click on load state, you'll get this option. Go to cell view and click on OK. What are the previous analysis values you did it will be loaded here, right? So instead of, you can avoid time typing all the setup, model libraries, analysis, transient, DC and all. That will be directly loaded here. Just click on this netlist and run. So for this, again you will get the transient as well as the DC, split the transient response. Now you have to go to tools and calculate. Here again you will get the values, but slightly different values, nearing the values of the delay and intersect you will get it. So again you have to do the delay and the intersect calculations. Go to the tools and calculator and follow the same procedure to check that. So you can do the delay calculation, and that will be slightly different from what you did it earlier. Do it for both TPHL and TPLH. Values will be slightly modified and noted down. Then you will get the intersect value also in the same way. Note down what are the differences between the first and the second value.